This special year, so to speak. We appreciate your coming here, and we have an interesting talks that span around deep learning, explainable AI, modeling, both from academia and industry, and I hope that it will be an interesting and fruitful session. I'll start and I'll give a talk, and I ask, oops, so it's not the right one. 1 second. Okay, so I will be talking about enhancing explainable AI. I assume that people know XAI, and the nice idea behind it that it is actually enhanced by a very old technique, actually 100-old, century-old technique of design of experiment that was invented, 100 years ago when we had the problem of data scarcity. So we didn't have enough data. Scientists didn't have enough data, and what they did is to create small designs, and they have to carefully design them in order to try and estimate even combinations of features that are not directly present in the experiment. And the nice idea is that you can actually apply the same techniques in the total opposite scenario when we have a huge amount of big data and we want to try and understand what are the importance and role of each feature. And this is a joint work with our student Aviv Notovich that already graduated, and Professor David Steinberg from the statistics department. My name is Irad. I am the head of LAMBDA. It's our lab at the engineering faculty that works with real data, real problems, and try to, again, bridge the gap between industry and academia. So this is a very known slide showing performance versus interpretability of models. So on the right, bottom side, you see decision trees that are very easy to understand, but are often very poor in terms of their performance. And on the top, you see, of course, the current models, state-of-the-art LLM, DNN, that are performing extremely well, but are very hard to interpret. And this is where explainable AI come into play. Instead of having, a black box type of model, there is some kind of interpretation, and most importantly, actually the designer, the user can give some feedback, and if he has some kind of knowledge, he can actually affect the model and try to direct it to obtain more insights. Okay, and this is a very known, again, example based on 6 million data samples of mortgage rate from Bank of England, trying to find which feature can actually predict, or which feature matters when we want to predict whether or not this loan will be returned. And what you see there are what is known as SHAP, or the use of Shapley values, that represent by those bars how each factor is affecting whether or not the loan will be returned, and whether it is affecting to the right or to the positive side or to the negative side. And this is a known technique. Now, the SHAP value is kind of straightforward. It is based on the idea that you want to estimate the effect of each feature on the model, on the ability to predict the model. And basically what you do, you look at all the different coalitions, all the different options of having these features and trying to see what happens when the model has a specific feature versus the case where it doesn't have this feature, and try to average it. And basically what you're trying to find is the marginal contribution of the feature, okay? And this is what dictates its importance, a global importance that is, of course, model dependent because you are using it within a model, but actually is working quite well since it preserves certain assumption like linearity. It adds to the total contribution. If there is a feature that doesn't add any information, it will obtain a 0 grade, and so on and so forth. The problem, and you can see it again if you look at the equation up there, is that it's very computationally intensive. So if you have a specific model and you want to find what is the contribution of a feature, you need to run the model, and the model can be a very complicated, LLM, with or without this feature, in order to find the contribution. And now think about a situation that you want to estimate the potential effect of a combination of an interaction of two features. The way to do it is actually to create a new demi-variable that will actually reflect all the combination, a Cartesian multiplication between these two features, and you can actually estimate this new variable in order to find what is the effect of this interaction. So it's very time-consuming or computationally complex. It's not actually built for high-order interaction. And also, you don't have a smart way to interact with it. And here comes this century-old idea of design of experiment. And it represented nice by this cube. If you have 3 features, you have, and each feature is a binary one, so you have overall 8 combination. It can be represented by this cube here. So every point there represent a combination of feature levels. And the idea of Sir Ronald Fisher in 26, actually even earlier, was to find only subsets of this high dimension, like those 4 points out of those 8. And the nice thing is that they are orthogonal to each other. It means that, if you represent them by a vector and you multiply them by a vector, a Curie vector, actually they are orthogonal one to the other. And the meaning in terms of information theory is that for every feature level, when you want to estimate the model with respect to the other level, all the other features are organized in the same way, so to speak. So it means that you can actually try to isolate the effect of each feature by itself. And if you introduce more and more such experimental points, you can actually estimate high-order interactions. Sometimes, or in many times, there is what we call a aliasing effect. So they represent also some other high-order combinations. But you know this aliasing structure, so you know in advance if you have a suspect of a certain combination that will work, you know how to design the experiment in a way that you will be able to estimate its effect, you know, in a isolated way, so to speak. So without going into the technique, there is a paper if someone is interested. We built a specific, what we call, again, design for experiment was the name. A DFX is designed for explainability. This is how we called it. A special DFX matrix that is orthogonal. And then after certain manipulation, we can compute the average response over this combination of you know, experimental combination. It's much more efficient than just selecting a subset randomly, as often people do when they try to overcome the complexity effect of SHAP. And the nice thing is that, as I mentioned, since those features are orthogonal to each other, those experimental conditions are orthogonal, you can actually estimate the effect of high-order interactions even without running again the model, simply by multiplying the relevant columns that represent those features, and based on that, those columns, these new columns that are, you know, have you know, a linear complexity, you can actually estimate the effect of that specific high-order interaction. And this creates a situation where you can actually explore and interact with the model as I showed before, with this feedback loop, that you are actually learning something, gaining insight, and then you can actually go to the next experimental phase with those insights in mind. So just to give you the notion of what I mean by multiplying, if you have a very, very small, you know, matrix here, you know, with only 6 features, and you have some kind of response based on this model, if you want to, for example, to find a potential effect of a high-order interaction based on feature 2, 3, 5, and 6, all you have to do is to multiply the relevant columns to get a new column that represents this combination, and then run a linear regression with respect to this column based on the average response. And when you do it, you'll get actually the coefficient of this linear regression will give you the effect of each factor and each interaction that you are interested to learn, again, simply by multiplying the relevant columns. And of course, it can be done in a way that you multiply it, you gain some insight, then you think, okay, maybe it's not really 2, 3, 5, and 6. Maybe I should get rid of feature number 5, and you just get the right column, and you get this insight. And this is done without having to run the model, which, again, this is the heavy stage that you need to do. And the results are quite nice. So first, when you look at the DFX, when you look at the relevant features with respect to the SHAP, they are not always the same. By the way, even if you run the same combination of SHAP with some kind of different initial point, it's not a unique solution, but there is a very strong correlation between those features that are found to be important between the two methods. And when you want to compare when they are not identical, and you want to compare how those features that were selected by DFX are performing with respect to SHAP, you see those two lines, the red and the blue, represent the DFX accuracy and the SHAP accuracy with respect to the y-axis, you see that they are very similar to each other. This line here, these two colors here represent the information, the mutual information between the selected feature and the output. The nice thing is when we select mutual information is that we are model independent. We don't, while here we are actually using a model, here we just look at the conditional relevant, conditional distribution of the output given the input, and we see again that the features selected, even if they are not the same, they have the same amount of information about the system output. So it's quite consistent, and the nice benefit is that it cost us, and this was actually tested over and over on real examples, it roughly cost us 1% of the computational cost of SHAP. So 2 orders of magnitudes can be saved, and again, we are talking about large deep networks that sometimes takes weeks to discover and to learn. Then having 1% of this computation time saves a lot of time and a lot of computation cost. So conclusion: XAI is of course important and emerging field, and will be and continue to be such in my view, as we use more and more complex model. The challenge in many of those methods are challenges that are related to the modeling, to the fact that they are model dependent. You can use old methods such design of experiment, again 1 year old, to try and apply it, even though the conditions are totally different. Those methods works very well, and it provides us not only this benefit of 1% of computational cost, but also the ability to interact very easily, actually extract more information from a given model without having to relearn it. So by that, I finish my talk, and thank you very much. Thank you. Any questions? Yes, please. Yeah. Okay. So you have a model, and you have one model we use features selected by SHAP, one model we use features selected by the DFX. Okay? And now we run it over a test set, and we just looked at the accuracy. You are right, I didn't explain the y-axis, and the x-axis is basically the number of features that you select. So if you select only one feature, the first feature by both of them, it's already a very informative feature that gives you actually around 78% for SHAP, and much less for the DFX, around 68. But with the second, third, fourth, and so on, they are very similar. So it means that as the number of features are growing, according to the marginal law of of the effect, you get all the information that you want. And the same goes with these two. In these two, you simply look at, let's say, 5 features. What is the mutual information between those 5 features, either selected by SHAP or DFX, with respect to the output? So it's model-free. So you cannot claim now that maybe the reason for them being equal is because the model cannot actually extract the right information from the feature, because it might happen that the model is, has its certain limitation. Whatever you feed won't change. But here it's not the case. It's model independent. So this is what you see. Yes? We applied it to convolutional neural networks and to conventional machine learning. We haven't applied it to LLM, but definitely the same idea can be applied then. Yeah, I mean, yeah, definitely BERT is one of the options, yes. Okay. 2 minutes or 2 questions? Okay, I think that anyway we are pretty much done. Thank you very much. And